You clicked on this video because you are wondering how new large language model architectures like KV sharing and multi-head compression are actually changing the game. The real stakes are that your current hardware choices based on raw compute speed might be completely wrong for the models you are deploying today. By the end of this explanation, you will understand why the bottleneck has shifted and what specific hardware requirements you must prioritize to keep your inference costs low. For years, the industry has operated on a simple assumption. When you want faster large language model inference, you need more floating point operations per second. We chased higher FLOPS ratings, believing that matrix multiplication was the only thing that mattered. We built clusters optimized for raw compute power, assuming that if we could just crunch numbers faster, the model would run smoother. But recent developments in architecture are fundamentally breaking this assumption. We are seeing a transition where the limiting factor is no longer how fast we can calculate, but how fast we can move data. Consider the standard operation of a large language model during the decoding phase. The system generates text token by token. As it does this, it builds a key-value cache. This cache stores the attention states of previous tokens, so the model does not have to recompute them for every new word. Traditionally, this cache was seen as a memory footprint issue, a necessary evil to enable speed. But as we look at innovations like joint encoding and multi-head compression, the picture changes. These techniques are so effective at eliminating redundant computation that the matrix multiplication step becomes almost instantaneous. Here is the thing. When you remove the compute bottleneck, the memory bandwidth becomes the new ceiling. If you are serving a model using joint encoding, you might see up to a 4.38 times compression of the key-value cache. This allows you to fuse similar blocks across concurrent requests. In practical benchmarks using VLLM, this translates to a 40% increase in throughput. That is a massive gain. But it also means the system spends significantly more time fetching data from memory than it does performing calculations. The hardware that was once considered overkill, with massive high-bandwidth memory pools, is now the critical component for performance. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Let us look at the specific mechanics of this shift. Multi-head compression and selective sharing strategies like DroidSpeak are designed to reduce the memory footprint by orders of magnitude. DroidSpeak, for instance, proves that cross-LLM sharing can reduce prefill time by 3.1 times and boost throughput by 4 times. This effectively mitigates the asymmetry between the compute-heavy prefill stage and the memory-bound decode stage. When you compress the data so aggressively, the time required to load that data from the memory hierarchy dominates the total latency. You are no longer waiting for the GPU to multiply matrices. You are waiting for the memory bus to deliver the compressed blocks. This reality forces a reevaluation of hardware requirements. If your workload is now memory-bound, a GPU with higher FLOPS will not help you. You need systems with massive HBM capacity and bandwidth. An 80 GB or larger memory pool per GPU becomes more critical than peak compute speed. The cost-performance trade-off curve has flipped. Systems that were previously optimized solely for peak compute speed are now less efficient than those prioritizing memory efficiency. The best inference server for long-context applications is no longer the one with the fastest theoretical compute. It is the one that can sustain the highest memory throughput. However, this transition is not without its complexities. While accuracy loss remains negligible, the system-level overhead increases. Maintaining shared representations across different model architectures and request types introduces significant complexity. You are now managing cache coherence and eviction heuristics that standard compute-centric monitoring often misses. Engineering teams must prioritize memory efficiency as a core architectural key performance indicator alongside latency. If you do not account for the complexity of managing these shared blocks, you risk introducing failure modes that are difficult to debug. Furthermore, the gains from these technologies are highly dependent on specific request patterns and concurrency levels. The memory-bound reality may not uniformly apply to all workloads. In scenarios with low concurrency or unique request types, the compute bottleneck might still exist. This means that while hardware designs must prioritize memory bandwidth, optimal performance still relies heavily on sophisticated scheduling algorithms. You need heuristics that can intelligently decide when to compress, when to share, and when to evict data. The memory-bound label is a generalization that holds true for high-throughput serving, but it requires careful management to avoid memory pressure spiking when the system tries to maintain too many shared states. The implications for production deployment are profound. If you are choosing hardware based on outdated benchmarks that only measure flops, you are likely making a costly mistake. You might be buying a machine that is perfectly capable of computing but starves for data, leading to poor cost-performance ratios. The shift to memory-bound inference changes the optimal hardware stack. It favors interconnects that support fast block-level data movement for shared key-value blocks over traditional high-bandwidth compute clusters. This redefines what the best inference server looks like for modern applications. We are moving into an era where the efficiency of the algorithm dictates the requirements of the machine. As compression algorithms eliminate redundant computation, the limiting factor becomes the memory bandwidth required to fetch and manage the remaining cache. This is a fundamental change in how we approach system design. It is not just about adding more compute, it is about orchestrating data movement with unprecedented precision. The future of large language model acceleration lies in the balance between these advanced architectural strategies and the physical constraints of memory bandwidth. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.